Hi everyone, this is a quick tutorial video on your upcoming exam in Pchem lecture, and specifically we're going to be talking about chapter 5 or enthalpy of mixings and so on. I'm just going to do a bit overview and here and there. Hopefully it makes sense to you, and at the end of the day I'm just making the video to help you guys out. So hopefully it helps. Anyhow, now that you're learning about mixing, there's a whole slew of new equation that you will see. Among other things is the Raoult's law, freezing point depression, vapor pressure, boiling point elevations, the osmotic pressures, and so on, and the lever rule as well. But before we go into each one of those, I just want to kind of go back and look at it in the big picture term. That is, whenever we're talking about chemical potentials and mixings and so on, whenever we have an equilibrium state, what we want to have is that the chemical potential of one phase is going to have to be equal to the chemical potential of the second phase, and that's when we reach equilibrium. Or if you want to look at it in terms of the derivative form, then the change in one phase minus the change in other must be equal to 0. So the question is, how does the chemical potential changes with respect to all the application that we're trying to do? Well, you've done from the Clausius-Clapeyron equations, so the pressure and temperature changes, is that the chemical potential changes with respect to pressure by a value of Vm. Whereas if we were to look at how the chemical potential changes with temperature, that's going to give us a negative molar entropy. So that was what you did in Clausius-Clapeyron equations, and essentially you're going to look at three different states. There is a solid, you have a liquid, you have a gas. So you can have a transition between gas and solid, solid to liquid, or liquid to gas. And then you're essentially looking for the temperature and pressure changes in each one. So you get three different equations. So 1, 2, and 3. Three distinct equations. Now, on chapter 5, we're going to introduce one additional changes, which is the changes in concentration. It's not explicitly written, but the chemical potential is changing with respect to concentration by a value of RT over chi, where chi here is our mole fraction. I keep saying concentration because mole fraction is fairly similar in terms of conceptually to concentration. It's not exact, but close enough. It's the vernacular that's easier to understand. So now we still have the same issue as well. We have solid to a liquid transitions, or in this case not exactly liquid, but more I should say solution. And we also have a gas transition. So now we have a solid to liquid, liquid to gas, solid to gas. But now there's additional confusion as well, because now there's three possible experiments, and then we can have changes between mole fraction with pressure or mole fractions with temperature. Now you can have the solids impure or the liquids impure between these two things, or you want to change, you want to look at the temperature change or the pressure change. Now you see from here you're going to start to see multitude of different kinds of experiments, and I think I was counting each one, and it comes out to about 6 different equations at least. So the combination becomes bigger now because you don't just look at 3 different things, but now you have impurities in the liquid phase or impurities in the gas phase, impurities in the solid phase, and whether you want to look at the pressure change or the temperature change, or you want to look at one or the other. So the equation that you see in this particular chapter 5 or the one in mixing is going to be quite numerous. But in the end of the day, the way to solve and derive of each of the equations are going to be the same. Now I'm not going to do a whole slew of video of derivations because there's too many derivations to do, and instead I'm just going to do one of the derivation, which is the easiest one, and the one that you are used to doing, which is the Raoult's law. So in the Raoult's law, and I promise this is the only derivations, and then we're just going to use the equation that's given to solve the problem. Okay, so in Raoult's law, we have our initial state is that we have a pure liquid and we have a pure gas. Right? So we have A in the gas phase and then A in the liquid phase. Now this is still pure. And then suppose that we were to change the concentrations of A. So now we have A in the liquid phase as well as impurity B in the liquid phase. And now we have A in the gas phase. It says, and we're trying to figure out how does the partial pressure changes with respect to concentration in the liquid phase. Okay, how does the partial pressure in the gas phase changing with respect to the concentration in the liquid? So let's kind of put in the equation. So we want to know, this is still a gas to a liquid transition. So we're trying to figure out the equilibrium between the two. So we want to know how does the chemical potential of the gas is changing and how does the chemical potential of the liquid is changing. So if we were to look at the gas, this is our initial pressure and it changes after you introduce impurities in the liquid phase. So the only thing that changes in the gas phase is that the pressure is changing. So if the pressure is changing, the chemical potential in the gas phase is changing by a value of Vm times dP. So how about the one in the liquid phase? Well, yes, if this is just pure A and B, the pressure on the surface of this liquid will also change because the partial pressure changing. So this is Vm of the gas, this is Vm of the liquid times dP. But there's also one additional thing, that is the concentration in the liquid phase is changing to some kind of new mole fractions. So I have to add the term on how the mole fraction is changing, and that's going to be an additionals of RT over chi d chi. And remember, equilibrium occurs when the difference between these two states is equal to 0. So if I were to subtract the top line here with the one on the bottom, I should get a 0. And a 0 is going to be equals to Vm of the gas minus Vm of the liquid times dP. And remember, this is 0 minus positive RT over chi. So it becomes negative RT over chi d chi. Okay. Now, I'm going to do one approximation, that is, if I have the molar volume of the gas and molar volume of the liquid, I'm going to assume the molar volume of the liquid is so small compared to the gas that it's more or less 0. So now we're simplifying equations that 0 is equal to Vm times dP of the gas phase minus RT over chi d chi. And I'm going to put another assumption that our gas is ideal. Okay. If you have an ideal gas, this molar volume is just RT over P dP minus RT over chi d chi. And this is again molar fractions of the liquid phase. Okay, so the temperature RT term can cancel out because they're the same. So what we have is now 1 over P dP is equals to 1 over chi d chi. And if I were to take the integral, because again we kind of have to solve everything, this comes out to ln of P final divided by P initial is equals to ln of chi final divided by chi initial. Now I don't like logarithm, so I have to get rid of it by using exponential. So if you take exponential in each one, you get P final over P initial is equals to chi final over chi initial. Now it's starting to look a lot closer to the equation that you've seen before. So if I were to solve it for P final, this is going to be equals to P initial times the mole fraction final divided the initial mole fraction. Well, remember our initial state, our initial here, is a pure vapor pressure as well as a pure liquid. Right? So if my liquid is pure, my initial mole fraction is just going to be equals to 1. And if my gas is pure, then the initial vapor pressure is just the pure, or the P star here. So P final is equals to P star times the mole fraction final of the liquid. That is the derivations of Raoult's law. Okay. And all we did here to derive the equations. I know you don't have to do this, but we're just keeping track. What's changing? So pressure is changing and concentration is changing both at the same time. So we add it up and subtract. We figure out what's changing, and we simply subtract one to the other and just go through with the rest of the derivations, and then we get to the equation that you see. So this is for Raoult's law. Now, like I mentioned before, the combinations is numerous, and I'm not going to do all of them because it just would take way too much time. But here are some of the one that you should remember or should write down in your note. Sorry, I'm going to skip that one. Okay, this one here. So the first one is the boiling point elevation. So if you have a boiling point elevation, the temperature is changing and the concentrations of the liquid phase is changing. And if you play around with the equation, you get this particular equation. That is, the change in the boiling point of the liquid is equals to R times the initial boiling point of the liquid to the power of 2 divided by delta H vaporization times chi of B, which is the number of moles of your impurity. So for example, a typical problem would be, or a simpler one would be, what is the boiling point of a solution of containing 95% water, that's an R there, and 5% sugar solution? This is 95% by moles and 5% by mole. So I'm just kind of making it easier for now. You know, you can find out, or you're given that the enthalpy of vaporization of the water is 40,500 kilojoules per mole. Oh, excuse me, the unit is not right either. And the boiling point of the pure water is just 100 degrees Celsius. So what is the new boiling point? Well, this is just the first step. The change in the boiling point is R, so 8.3145. You want to use the one that has joules in it, times the initial boiling point, 373 Kelvin. Don't forget to convert it to Kelvin. So we're putting that information there, divided by the enthalpy of vaporization, so 40,500 joules per mole. Again, don't forget to convert this to joules as well. And then we're going to multiply it by the mole fractions of the impurity. This is my impurity. And my impurity is the sugar, so I put in the 5% of the sugar impurity. Alright, so that's kind of the simple equations and the simple problem that you have. That's the boiling point elevation. Now, the second equation that I want to show is the freezing point depression. And if you look at that equation here, and that one on the top, they're the same. It's just, I'm just changing the enthalpy of vaporization to entropy of fusion, and I get an entirely different equations, or the derivation is the same, but now I'm just talking about the fusion instead of vaporization. So an example would be, what is the new melting point of a solution containing, I still have the same typo, sorry, 95% water and 5% sugar solutions, if you're given that the enthalpy of fusion is 6,000, like I said, same typo, 6,000 joules per mole, and you know that the melting point of the liquid, or sorry, melting point of the solid is initially 0 degrees Celsius to 73. Okay, so we have R times the initial melting point, so 273 to the power of 2, divided by, so this is T squared, divided by 6,000 joules per mole, which is our enthalpy of fusion, delta H. Fusion times 5%, which is the number of moles of the impurity in the liquid phase. Alright, so impurity in the liquid phase. Okay, so that's it. Plug and chug, plug and chug. So now we're talking about, in this case, a solid to liquid transitions where the liquid is not pure. Then we can keep going, and we'll do another one here. Whoops, there's supposed to be a separation there. How about a solubility? That is, we're talking about, instead of the freezing point of the liquid, I'm talking about the solubility of the solid now. If one were to kind of look at the equation, then this is the equation that you get. The mole fractions, the new solubility, so new mole fraction solubility divided by the initial mole fraction solubility is going to be equal to delta H over R, 1 over T final, sorry, there's a lot of typo there, minus T initial. So suppose that you know, or you were given that the solubility of sugar is 3 moles per 6 moles of water at 298 Kelvin. Given that the enthalpy of solubility, so when you mix sugar and water, it gets slightly warmer, so it's negative 10 kilojoules per mole. Calculate the new solubility at 320 Kelvin. Okay, so how do we solve this whole thing? Let's just plug in some of the number. Yes, there's a bunch of algebra involved, but here it goes. So I want to solve for the new solubility, which is my KFB final, divided by the initial mole fractions. And the initial mole fraction is that I have 3 moles of sugar per 3 plus 6 moles total. Right? So I have 3 moles of sugar and 6 moles of water. So in solution here I have 9 moles in total. So that's why it's divided by 9. And that's going to be equals to delta H divided by R 1 over T final. So I want to know the solubility at my final temperature of 320 Kelvin, minus 1 over the initial temperature. All right. Now plug and check. You have to take exponential to solve this whole thing, but you know, a lot of it is plug and check. Oh, right. So this is T final. Sorry. Make sure that you have the right number. So that's one. The next one is the osmotic pressure. This is also another important equation. So for example, if you have a solvent here and your solvent is pure, and then you have a highly concentrated solution, what happens is that there's a lot more entropy here, for the fact that you have impurities. So what happens is that in order to reach equilibrium, if this is just a regular diffusion, then the dye would come out. But since you have a semi-permeable membrane that prevents the dye from moving away from the container, water is going to rush up instead to decrease the overall concentration. So that's the osmotic pressure. And then the equation that's written to you is this one here. So this is the derived equation. But your book gives it to you in terms of this particular fashion, which is fine as well. That is, this is an approximated version, but it's all right. That is, the negative R times temperature times the mole fractions of your impurity is equals to the molar volume times the osmotic pressure. And the one to remember is that your osmotic pressure, P, is going to be equal to rho GH. So rho is the density, G is the gravitational constant, and H is the height of how high the water is going to move up. And the rest is just plug and chug. So for example, you can either be given a question that solves for rho, which is calculate the osmotic pressure, or you can be asked to solve for the height. So it's either one of each. Okay, so this is the first version of the video. It's already taken me about 18 minutes. So I'm going to make the next one. I have to organize it a bit more, but the next version is going to be a bit more about Raoult's law, lever rules, and phase changes. I do want to separate it out so that it's easier to manage one at a time.